Okay, this is about sequences. So a sequence is just a list of numbers. So typically it starts at A1. It could start at A sub 0 or really anything, but I'll have this one starting at A sub 1. And in this class, we're going to talk about infinite sequences. So wherever it starts is wherever it starts, but it goes forever. So there's an A sub 2, A sub 3, and it goes forever. The subscripts are only going to be integers. And typically, and we'll see examples, but typically we have a formula for A sub n. And one thing we talk about with sequences are limits of sequences. So we say that the limit, and this is a technical definition. So I'm going to use the letter epsilon. You might remember definitions like this from Calc 1. But we say the limit as n goes to infinity of A sub n is a number L if for every positive epsilon, there's an integer big N such that whenever little n is at least big N, we have that the difference between A sub n and L is less than epsilon. In other words, epsilon is how close we want the term of our sequence, and the term is what we call A sub n. Epsilon is how close we want the term of our sequence to be to L. And what this is saying is no matter how close we want it to be, if I take a large enough n, meaning that there's a big N such that whenever little n is at least that big, we get what we want, meaning that the distance from the term of our sequence to L is closer, at least as close as we want it to be, so it's smaller than epsilon. Okay, so this is similar to the definition that you saw in Calc 1. By the way, we can also say that the limit of a sequence is infinity. We can also say that it's negative infinity. I'll just give you a formal definition for when the limit is positive infinity. But we say this limit is positive infinity, roughly speaking, if for large values of n, this just gets larger and larger, at larger than you would ever want. More formally, big A is going to be how large I want the term to be. And what this says is for every big A, there's an integer big N, such that whenever little n is at least big N, the term of our sequence is greater than big A, which is this number that we're allowed to name. So if you tell me that big A is 1,000,000, then I have to be able to say, well, if n is at least however big, and I get to name whatever I want for big N, but it has to be the case that as long as little n is however big I say it should be, that the term of our sequence is bigger than 1,000,000, if you told me that big A is 1,000,000. Or you could tell me that big A is 1,000,000,000 or 1,000,000,000,000, or the point is you could say whatever you want. But the point is, eventually the terms of the sequence have to be that big, no matter how big you tell me that you want them. That's when the limit is infinity. The limit would be negative infinity if I just put a less than there. Anyway, let's find some limits. So these pretty much work the way you would think that they work. We've done limits before. The one thing to think about that usually doesn't matter, but sometimes it does, is that when we're talking about sequences, and in particular when I'm using the letter n, I'm going to be careful about using the letter n to represent integers. So we're imagining an integer that's getting larger and larger, going to infinity, and then doing 1 over that integer. Most people are probably just thinking this should just be 0 because it's like 1 over a huge number is about 0. And that's right. The fact that n has to be an integer here doesn't really have any effect. if n could be any real number, like it didn't have to be an integer, it's still true that 1 over a huge number is a tiny number. And that doesn't change whether we're talking about 1 over a huge real number or 1 over a real number that happens to be an integer. 1 over any huge number is about 0. So nothing changes there. Here's another example where the fact that n is an integer really doesn't matter. Roughly speaking, the square root of a huge number is a huge number, whether we're talking about an integer or not. This limit is infinity, and this is the same as if we were talking, if n were allowed to be a real number, or if n has to be an integer, this answer is the same. So nothing surprising there, but okay, now look at the third example. For this one, it's going to matter that we're talking about a sequence. I'm using the letter n, and again, I'm going to be careful about, if I use the letter n, I intend for n to be an integer. This is a function where, let me just sort of doodle off to the side here. So this isn't the world's best graph, but this is good enough for us. If I draw the graph of y equals sine of pi x, like I replace the n with an x and I allow x to be a real number, of course this is a sine function, and so the pi has some effect, but I'm not really drawing that accurate of a picture anyway, so what I'm getting at is this just goes up and down forever. So if I were doing the limit as x goes to infinity of sine of pi x, and by the way, I'm using the letter x here because I want to allow x to be a real number, I would say this limit does not exist because this is a function that just, it doesn't get closer and closer to any particular number as x goes to infinity. It just goes up and down forever. However, this limit is going to exist because actually, when n is an integer, this always gives me 0. Right, like, just to remind you, sine of 0, sine of pi, sine of 2 pi, sine of 3 pi, so on. They're all just 0. Sine of any whole multiple of pi is 0. So if I like, I can just say I'm simplifying it. This is always just 0. When n is an integer, this is always just 0. So this limit exists and it's just 0. So I just wanted to show you an example where it can matter that n is always an integer when you're doing a limit. Because if x was allowed to be any real number like we did down here, we'd get a limit that doesn't exist. But this is an unusual example. I'm doing it on purpose to show you that this happens sometimes. In practice, most examples are like the first two. So the next theorem is kind of just a formal way of saying something relevant to what I was just talking about. We often have a formula for a sub n, and we could call that f of n, like it's just a function of n. And a lot of times we're talking about a function that would make sense to plug in a non-integer for, even though we're using the letter n, so we're only really talking about plugging integers into it. But the function that is given in the formula could make sense if you plug in a non-integer, like these examples that we just did. When I'm looking at this one, n is always an integer because I'm using the letter n, but 1 over n would make sense if if n was not necessarily an integer. You can do 1 over something that isn't an integer. That's fine. So if you're in a situation like that, so we have some function f that can take a real number. So we're allowed to plug in real numbers for f. And if we do the limit as x goes to infinity of f of x, and keep in mind when I'm using the letter x is allowed to be a real number. So if I do the limit as x goes to infinity, and that's L, but what I actually want to do is the limit as n goes to infinity of a sub n, that's also going to be L. So, yeah, that's something that we can use. We'll see an example in just a second. But let me go over a couple of what we can call limit laws. So these are ways of combining sequences that we already know the limit of. So if I know the limit of a sub n is a and the limit of b sub n is b, then I can do the following. So the limit of a sub n plus b sub n, that's just going to be a plus b. Limit of a sub n times b sub n, that's just going to be a times b. In fact, I can do the limit of any function of a sub n as long as it's a continuous function, or more specifically, it doesn't even need to be continuous everywhere. As long as it's continuous at a, at big A, then this limit is going to be f of big A. I mean, it makes sense. Little a sub n is going to big A, so what do I get? I get f of big A. Okay. So let's use that to do an example. It's maybe a little bit more complicated than the previous ones we did. So I want the limit as n goes to infinity of, say, this. I can break it down. First of all, I can break it down according to this first rule. So when I have addition happening inside my limit, I can basically just do the limit of one part plus the limit of the other part. As long as all these limits exist, I can do that. So I can break this apart. I can do the limit as n goes to infinity of 3. I can do the limit as n goes to infinity of this part and this part separately. And as long as I get finite answers for all of these, I'll be set. So here I go. So here's 3. That's really easy. 3 is just 3. As n goes to infinity, the limit of 3 is just 3. Let's talk about the second one. 1 over root n as n goes to infinity. So root n goes to infinity. We talked about that a minute ago. Roughly speaking, the square root of a huge number is a huge number. So as n goes to infinity, this is basically like 1 over a huge number, so we should think of this as going to 0. And sine is a continuous function. So we can use this. So sine is a continuous function, and the thing I'm doing the sine of is going to 0. So this should just give me sine of 0, which is 0. So we keep moving. So let's do this last part. This last part is what we would call an infinity over infinity form. Because as n goes to infinity, natural log n goes to infinity, and the bottom clearly goes to infinity. So what we can do is L'Hopital's rule. Especially because, so let me get a new sheet of paper. So we are about to do L'Hopital's rule. When we do derivatives, which we're about to do because it's L'Hopital's rule, I want to do the derivative of a real valued function meaning a function that takes a variable that does not have to be an integer. Technically speaking, taking a derivative of a function that can only take integers doesn't make a lot of sense. So I'm going, and this is a fairly superficial thing, but I'm doing this for emphasis just because I use the letter x in a limit to represent a real number, and I use the letter n to represent an integer. So I'm about to take derivatives, so let me emphasize that this is like a real valued function. And when I write this, x doesn't have to be an integer. X could be any real number. But using L'Hopital's rule, derivative of the top is 1 over x, derivative of the bottom is just 1. And now I look at this again, and x is going to infinity, so I get 0. So we are using this theorem, the one that says that if we're talking about a function that could take a real number, and if I do the limit as x goes to infinity of this function, I get a certain answer, then the limit of the sequence gives me that same answer. That's what we just did. We took this function, which can take a real number x, and did the limit and got 0. So the limit, now the limit with n's in it is also 0, where n has to be an integer. So let's put our final answer together. So we had this plus this plus this, and we did these separately. This is 3, this one went to 0, and this one we just figured out also goes to 0. So 3 plus 0 plus 0